Hello, grade 12s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Uabudiwa Sos Ugobela Wemets. And without any further ado, let's look at these questions that we have here. Okay, so we have question 8. It says grade 12 physics learners are conducting an experiment to determine the EMF and internal resistance R of a battery. They have access to an ammeter but do not have a voltmeter. They set up the circuit shown in the diagram below. So they could only get an ammeter, then they have no voltmeter, meaning that their challenge here is to calculate the voltage. Then 8.1 says define the term EMF of the battery. We have already defined that a couple of times. Let's go and check it out. So we say EMF of the battery is the maximum energy provided by the battery per coulomb of charge passing through it. Right. Then 8.2 says state the purpose of placing the switch next to the 8 ohm resistor. Why is it that we place the switch next to the 8 ohm resistor? So our reason for that is we need to control the current in the circuit by adjusting the resistance, right? So we're flowing to this path here. So that means we have adjusted the resistance in that way because we'll only have resistors that are now connected in series, right? So that's the whole purpose of putting a switch there. Right, then let's go to 8.3. It says use the results from the experiment to determine the internal resistance of the battery and the EMF of the battery using this equation is equals to I bracket R plus R. Right, so we have a 5-mark question here, and then this is what we call an interesting question. You know what is an interesting question? This one here, I know that gave a lot of you a challenge. So now I'm going to break it down for you. The way you were supposed to calculate the internal resistance here is by using simultaneous equations. I know that every time we mention simultaneous equations, a lot of you just get so angry because you don't want any questions to do with that. But then I will take you through how you were supposed to do that, and you will see that it was just an easy process, right? Now, remember, let's gather our facts. We know that the EMF and the internal resistance are always constant. In whatever situation, whether the current is flowing or it is not flowing, your EMF and your internal resistance never change. So when you buy a battery and then let's say, for example, it reads 12 volts. So it will always stay like that. Whether you decide to connect many resistors into the circuit or less resistors, the EMF remains the same. It will always be 12 volts. And the internal resistance of the battery comes along with the battery. So it will always remain constant. It never changes, right? So that means in our simultaneous equation, the E and the R here, this acts as our X and Y. Remember, in a simultaneous equation, you have to have two unknown variables, right? Now, remember, again, it goes back to the fact that whenever you have a 5-mark question, understand that you always have two unknown variables, right? Okay, so in this case, we do understand that we have two situations. First, when the switch is open, and second, when the switch is closed. Now, when the switch is open, this is what is happening, right? Current does not flow to this 8 ohm resistor here. So that means we only have this 8 ohm and the 0.4 ohm of the bulb being our effective resistance, right? So the current is just only flowing in this path here if the switch remains open. So we can see that there's only one pathway for current to flow. There is no splitting of the current. So that means both the 8 ohm and the 0.4 ohm are connected in series, right? So what we can do is just mainly say E is equals to I and then R plus R. Remember, they said we must use this formula. Now we don't have the EMF. We know it's an unknown. Then our current we are given when the switch is open. So let's indicate here switch open, right? So that we understand when we are calculating. So here switch is open, the current is 4. But then what is the external resistance? It has to be the 8 plus the 0.4 here, right? So which will give us 8.4. And then the internal resistance we do not have. But then what we are going to do now, simply just multiply inside with this 4. So 4 multiplied by 8.4, that's 33.6. Then 4 multiplied by r, that's 4r. Now, since we don't have e and r, let's just call this equation number 1. Remember, in order to solve a simultaneous equation, you have to actually generate the equations, right? Okay, so now let's go to when the switch is open, right? So let's say closed. Let's go to when the switch is closed, right? So if the switch is closed, now we understand that the current changes to 6 amperes. So if the switch is closed, now we have a splitting of the current at this position here. So some of the current splits and goes this direction, and then some of the current splits and goes that direction. So now the 8 ohm resistor is back, right? So now, meaning that in order to get the R external when the switch is closed, this is how we would get the R external. So let's first start by calculating the R external, and then it's R parallel plus the R series, which means we must first get the R parallel, easy peasy, R1 multiplied by R2 over R1 plus R2. Right, so let's multiply here. The R1 is 8, so that's 8 multiplied by 8 over 8 plus 8. When you punch that into your calculator, you get 4, right? Now, the R external, you have to add. So R external, remember, it's RP plus RS. The R parallel is 4, and the R series still remains the bulb, 0.4. So that means our R external is now 4.4 ohms, right? Now let's note, this is when the switch is closed. So let's calculate using the EMF formula. So we will have E is equals to I, and then R plus small letter r. The current when the switch is closed is 6. The R external, 4.4, and then the R internal we do not have, right? So the EMF now 6 multiplied by 4.4 is going to be 26.4. And then 6 multiplied by R, that's 6R. Then now we have created equation number 2, right? Now, since both equations have E as the subject of the formula, and we are saying E is always constant, meaning the E when the switch is open and the E when the switch is closed is the same. That means we can equate equation number 1 and equation number 2. So basically for a simultaneous equation, once you are able to generate equation 1 and equation number 2, you are done. It's just a matter of equating the two. Then equate equation 1 and equation 2, right? So equation 1 is 33.6 plus 4R, which is equals to 26.4 plus 6R. Now we know what to do. All the variables, all the constants one side, and then all the numbers with the variable one side, right? So from subtracting these ones, what do we get? We get 7.2, and then 6R minus 4R, that's 2R. So to calculate, we then need to divide both sides by 2. Then our internal resistance becomes 3.6 ohms, right? And that's just how you were supposed to calculate your internal resistance for 5 months. So note, it was a simultaneous equation. First get equation number 1, and then get equation number 2. You equate the two, then voila, you get your internal resistance. So make sure that you play the video as many times as possible and just try to understand the approach that I took into solving this one, right? Then for 8.3.2, it's now pretty straightforward. It's just a matter of choosing any of these two equations here in order to calculate your EMF. So now that we have equation number 1 and equation number 2, we can just take the value of R and substitute in here. So let's do it. In order to show you that it will be the same answer, I will just substitute in both of these equations. So we have equation number 1, it was 33.6 33.6 plus 4R. This was equation number 1. So let's substitute our value for R. That's 33.6 plus 4. The R, we got 3.6. Now, if you punch all that into your calculator, your EMF is going to be 48 volts, right? Or if you had taken equation number 2, you could have said 26.4 plus 6R. Then again, it's 26.4. And then where there's R, you will substitute the 3.6, right? And then again, when you punch into your calculator, you get 48 volts. So either way, you could have got your EMF as 48 volts, whether you substituted in equation number 1 or you substituted in equation number 2. So that's essentially how you were supposed to tackle this question here. So awesome. But then we are still not done. The question still continues in the next page. Okay, so now we have 8.4. It says calculate 8.4.1, the power dissipated in the battery when the switch is closed. Note that the power dissipated in the battery, right? So we are only concerned about the battery, and then it's only 2 marks. Now, when the switch is closed, if we can just go back here and look at the current when the switch is closed. So again, when we check here, when the switch is closed, we can see that the current was only 6 amperes. Remember, with current, there is no internal current or external current. Current is the same from the battery and throughout the circuit, right? So in order to calculate the power, we can just go for the formula that says power is equals to I squared multiplied by R. But then note that the R that we'll be using here is basically the internal resistance. So if you can just allow me to edit this one. Okay, let me first start by writing it and then now rearrange so that you understand that I will be using the R internal since I'm looking for the power dissipated in the battery. So the battery has internal resistance. Now the current is 6 amperes and then the internal resistance, remember we did calculate and then we found that it was 3.6. So understand that, right? Then having to calculate there, we get our power as 129.60 watts. Right. Okay, so this was 8.4.1. Okay, then 8.4.2 says calculate the energy dissipated in the bulb, in the what? Bulb, in 6 minutes when the switch is open. Right, so let's erase here. When the switch is open, let's go back and look at our current. So when the switch is open, they say the current is 4 amperes. Now, since the bulb is connected in series, we know that a resistor or a bulb that is connected in series will receive the full current or the total current. So that's 4 amperes because total current is equals to the current in the series. We know that. Okay, so now in order to calculate the power dissipated in the bulb, we can use, so it's the energy. So energy is simply W, that's power multiplied by delta time. So the power formula that we can use is again I squared multiplied by R, then that will be multiplied by delta time. But then again, remember that our delta time should always be in seconds. So the first thing that we're going to do, let's convert the 6 minutes to seconds by saying 6 multiplied by 60. That's 360 seconds, right? So the current, we said it's 4, so that's 4 squared. And then the R, that's the resistance of the bulb because we are calculating the energy dissipated in the bulb. So the resistance of the bulb is only 0.4. Then the time is 360, right? Now, when you punch all of that into your calculator, you get 2,304 joules. So that becomes the energy, right? Remember, energy is measured in joules, right? The SI unit. Okay. 8.5 now says, how is the brightness of the bulb affected when the switch is open? State only brighter, dimmer, or no change. Explain the answer. Now let's go back to our circuit and try to figure that out. So they're saying switch S is open, meaning that again, current is only flowing through the 8 ohm resistor and the bulb. And then since there's only one pathway for current to flow, we say these two components are connected in series. Now, what happens if they're connected in series? Our R external increases to 8.4 because we are going to say 8 plus 0.4. So now from that, we can observe that obviously there is an increase in the R external, or you can say there's an increase in the R total, because if you now say 8.4 plus the 3.6 that we found, then obviously there is that increase. So 8.4 plus 3.6, that's now 12 ohms. So number one is that there's an increase in the R total, but then we know the relationship of the resistance and the current is inversely proportional. So if there's an increase in the total current, then if there's an increase in the total resistance, there is a decrease in the total current. Pardon me for that. But if we are to comment on whether the bulb will be dimmer, brighter, or there will be no change, that's basically talking about power, the power that will be dissipated by the bulb. Now, what is the relationship of the current and power? We know that power is directly proportional to current. So if current decreases, then power also has to decrease. And if power decreases, that means the bulb will end up being dimmer. Right. So that's the explanation. Now, how do we then put it in words? How do we then put it in point form? Let's find out. So this is how we'll be putting it. Say dimmer, so a mark for that. The total resistance in the circuit increases, but then we know R is inversely proportional to current, so current decreases. Then P is directly proportional to I, so that means power dissipated by the bulb decreases because current also decreases. That's how you were supposed to explain that, and that's also how you were supposed to tackle all of this question for a total of 19 marks. So make sure that you revisit the video again, especially to watch that question there on the simultaneous equation. So, but then with all that being said, please press the thumbs up button if you have enjoyed the lesson and then you found it helpful. And if you've been watching the videos and haven't subscribed yet, what are you waiting for? Please smash that subscribe button. But most importantly, please share the link with your friends and classmates so that they may also find assistance. Remember, do not be selfish. We are winning as a team.